Hello friends, I welcome you in lecture number 3 on recurrence relations. In this lecture, we are going to discuss the method of solving linear homogeneous recurrence relations with constant coefficients. First, we will understand the method and then we will see two examples to understand the method. So first we recall what is linear homogeneous recurrence relation of degree say k. So a linear homogeneous recurrence relation of degree k is the recurrence relation which can be written in this form: an equal to c1 times an minus 1 plus c2 times an minus 2 and so on plus ck times an minus k. And if this ck is non-zero, then this is linear homogeneous recurrence relation with constant coefficients of degree k. If this coefficient ck is non-zero, then we say that we have a recurrence relation of degree k. Now the solution of this recurrence relation is the sequence an such that we have some formula for nth term of the sequence, for which an sequence an is a solution of this recurrence relation given by number 1. So first we will assume that this recurrence relation has a solution in some particular form. Suppose solution of this recurrence relation is in this form: an equal to say r raised to n, where r is a real or complex number or real or complex variable. We have to decide that for which value of r this an will give the solution of this recurrence relation 1. So we assume that suppose an equal to r raised to n gives us this sequence an, which is the solution of this recurrence relation 1. Now if this is the solution, then it will satisfy this recurrence relation. So we can substitute an equal to r raised to n. This is equal to c1 times an minus 1. If an is r raised to n, an minus 1 is r raised to n minus 1 plus c2 times an minus 2. An is r raised to n, so an minus 2 is r to the power n minus 2 and so on. ck times an minus k is r to the power n minus k. Now here we can divide this equation by the lowest degree. Here we can see in this term degree of r is lowest, so we divide this equation by r to the power n minus k, or we can say that we divide this by r raised to n minus k, or we multiply this by r to the power negative of n minus k, that is we multiply by k minus n. We multiply each term of this formula or this equation by r to the power k minus n. So I am writing here r raised to n is multiplied with r raised to k minus 1 equal to c1 times r raised to n minus 1 times r raised to k minus n plus c2 times r raised to n minus 2 times r raised to k minus n and so on plus ck times r to the power n minus k into r to the power k minus n. Therefore here we can see r raised to n plus k minus n, that is r raised to k, equal to c1 times, here also n will get cancelled and we are left with r to the power k minus 1 plus c2 times r to the power n will get cancelled, k minus 2 and so on, ck times r to the power 0, that is 1. K will get cancelled, n will get cancelled. And let me rewrite this by considering all the terms on the right hand side. we transfer on the left hand side, r raised to k minus c1 times r raised to k minus 1 c2 times r raised to k minus 2 and so on minus ck equal to 0. So we obtain this equation which is in powers of r. It is a polynomial equation in powers of r, and this equation is called characteristic equation of given recurrence relation. Characteristic equation. So what we have seen, we started by assuming that an equal to r raised to n is a solution of this recurrence relation. Therefore, we substitute an equal to r raised to n in this recurrence relation and we obtain this equation. This means an equal to r raised to n is a solution of recurrence relation if and only if r is a solution of this characteristic equation. So we have to solve this characteristic equation. Solving this characteristic equation, we will have k values of r, because this is polynomial equation in r. So we will have k values of r, say r1 r2 up to rk, and there are different possibilities that these values can be real and different. Some values can be repeated and we may have complex values also. So depending upon the nature of values of r which we will obtain by solving this characteristic equation, we have different formulas for the solution of recurrence relation. We have assumed that solution of recurrence relation is given by an equal to r raised to n, where this r is a solution of the characteristic equation, and the values of r which will satisfy this characteristic equation are known as characteristic roots. Characteristic roots means the values of r which are solution or roots of characteristic equation. So this is the method of solving recurrence relation which is linear, homogeneous and having constant coefficients. We assume that an equal to r raised to n is a solution of this recurrence relation, and we find that an equal to r raised to n is a solution of recurrence relation if r is a solution of characteristic equation. So what we have to do every time whenever we have linear homogeneous recurrence relation, we have to write down the characteristic equation corresponding to given recurrence relation, and then we have to solve that characteristic equation. And depending upon the nature of roots of characteristic equation, or depending upon the nature of r values, we will have different formulas for the sequence, for the nth term of the sequence an, which is a solution of recurrence relation. So first we are going to consider recurrence relations of second degree, and then we will generalize the method for recurrence relation of any degree. So I am writing recurrence relation of second degree, which is an equal to c1 times an minus 1 plus c2 times an minus 2. So first what we are doing, we assume that solution is in this form. So we can substitute an equal to r raised to n in this recurrence relation. So if I put an equal to r raised to n, I have r raised to n equal to c1 times r to the power n minus 1 plus c2 times r to the power n minus 2, and then I divide by lowest degree of r, or I multiply by r to the power minus of n minus 2 or r to the power 2 minus n. So I am multiplying each term by r to the power 2 minus n. c1 r raised to n minus 1 r to the power 2 minus n, c2 r raised to n minus 2 r to the power 2 minus n, and what I obtain, r square, n will get cancelled, equal to c1 times, here also n will get cancelled, and r raised to 2 minus 1, that is r, plus c2 times r raised to 0, that is 1. So I obtain r square minus c1 into r minus c2 equal to 0. I obtain characteristic equation of recurrence relation of degree 2, which is a quadratic equation in real variable or complex variable r. This characteristic is quadratic equation in variable r. Now every time to write down recurrence relation, you don't have to write down all these steps. If you can understand that here degree of this recurrence relation is 2, so we can write characteristic equation corresponding to this recurrence relation by starting with second power of r, because here degree is 2. So I replace an by r square, and I am taking all these terms on left hand side. Minus c1, I keep c1 as it is, but I am writing on left hand side, so it is negative. And here I have n minus 1, so I will write 1 power of r and minus c2 equal to 0. So because I have recurrence relation of degree 2, characteristic equation must also be of degree 2, or characteristic equation must be a polynomial of degree 2. So in this way we can write down the characteristic equation corresponding to given recurrence relation. And if you are not comfortable directly, you can substitute an equal to r raised to n and then divide by lowest degree term, and you will obtain your characteristic equation. Now if I have quadratic equation r square minus c1 into r minus c2 equal to 0, then the roots of this characteristic equation are called characteristic roots, and we will have two values of r which are roots of this equation. So suppose two values of r are denoted by say r1 and r2, and there are different possibilities that these two values are real and different. They can be real and equal, and they can be complex also. Suppose we consider r1 r2 are real numbers, and suppose they are distinct, that is r1 is not equal to r2. Now in each case we have explicit formula for the nth term of this sequence an, which is a solution of given recurrence relation. So we are writing that explicit formula. If roots of characteristic equation are real and distinct, that is r1 and r2 are real numbers and they are different, then the sequence an is a solution if its nth term is given by an equal to some constant, say alpha 1 times r1 raised to n plus alpha 2 times r2 raised to n. We have assumed that our solution is in this form, an equal to r raised to n. So here I have two roots, two values of r1 and r2, and both are real and different. So if I have this type of case in which I have real and distinct roots, then here I have to write r1 and r2 in place of r, and I multiply them by arbitrary constants, say alpha 1 and alpha 2, and here our n can take the different values, n equal to 0, 1, 2 and so on. This alpha 1 and alpha 2 are arbitrary constants. So this is the first case, and this is the formula for the nth term of the sequence an, which is a solution of recurrence relation. Second case is, suppose I have case 2 is r1 and r2 are real numbers but they are equal, that is roots are real and equal. In the case of real and equal roots, in this case we will modify these formulas because I have r1 equal to r2. So if I am writing say r2 equal to r1, then according to this formula I have alpha 1 into r1 raised to n plus alpha 2 into r1 raised to n. I am taking r2 equal to r1. But if I take r1 raised to n common, then I will have alpha 1 plus alpha 2 times r1 raised to n, and this is only one essential constant. And remember, if we have recurrence relation of degree 2, then in this solution we must have two arbitrary constants. Similarly, if we have recurrence relation of degree k, then we will have alpha 1, alpha 2 up to alpha k arbitrary constants in the solution. So we have to modify this formula. So to make these two functions independent, I have to multiply by n at any one place. Either I can multiply r1 raised to n here by n or here by n. So here I am taking multiplication by n, and n can take the values 0, 1, 2 and so on. So remember this formula. This is the solution in case of real and equal roots of characteristic equation. And if we have real and distinct roots, we will write an equal to alpha 1 times r1 raised to n plus alpha 2 times r2 raised to n. And we are not considering third case. Third case is r1 and r2 are complex numbers, but that is not in our course. So we are not going for complex roots. That is, we will consider only two possibilities, that either r1 r2 are real and different, and r1 r2 are real and distinct. So remember, this is very easy to understand. To find out the solution of recurrence relation, you have to first write down the characteristic equation corresponding to given recurrence relation. Suppose this is our recurrence relation, then first we have to write down the characteristic equation. If recurrence relation is of degree 2, then characteristic equation is a polynomial of degree 2. And here, corresponding to this recurrence relation, I have written r square minus c1 into r minus c2 equal to 0. And this is what I have discussed just now. Equation 2 has two roots, say r1 and r2. First possibility, r1 and r2 are real and different. Then sequence an is a solution of recurrence relation with an equal to alpha 1 times r1 raised to n plus alpha 2 times r2 raised to n. N can take the values 0, 1, 2 and so on, where alpha 1 and alpha 2 are constants. If we have equal and real roots, then solution is given by an equal to alpha 1 r1 raised to n plus alpha 2 n times r1 raised to n. Here I have multiplied this r1 raised to n by n so that these two functions become independent. This we can rewrite by taking r1 raised to n common, and I have alpha 1 plus alpha 2n in the bracket. So using these two cases, we consider these two examples. Here our recurrence relation is given by an minus 1 minus 2 times an minus 2 equal to 0. First step is we have to write down the characteristic equation. So the characteristic equation is r square. Here coefficient of n is 1, so we consider coefficient of r square as 1. Here coefficient of an minus 1 is minus 1, so we write minus r, and minus coefficient of an minus 2 into r raised to 0. So this is the characteristic equation corresponding to this recurrence relation. If you are not comfortable in writing directly, what you can do, substitute an equal to r raised to n in this equation and then divide by lowest degree term of r. Now we solve this quadratic equation. We can see that I can rewrite this minus r as minus 2r plus r minus 2 equal to 0, and now I can rewrite this as, I take r common, I have r minus 2. Here I can rewrite this term as 1 into bracket r minus 2 equal to 0, and r minus 2 is common, so I have r minus 2 times r plus 1 equal to 0. Therefore we have two roots, r equal to 2 and r equal to minus 1, and we can see both the values are real and different or real and distinct. So therefore the solution of recurrence relation, the solution of given recurrence relation is an equal to alpha 1 into r1 raised to n. We can consider r1 equal to 2, so alpha 1 into 2 raised to n plus alpha 2 into r2 raised to n, r2 is minus 1, and n equal to 0, 1, 2 and so on, and this alpha 1 and alpha 2 are arbitrary constants, where alpha 1, alpha 2 are arbitrary constants. Now we consider second example. Here this is also recurrence relation of degree 2. So first I rewrite this as an minus 6 times an minus 1 plus 9 times an minus 2 equal to 0. Now I can write the characteristic equation of this recurrence relation in this way. The characteristic, I can shortly write characteristic equation is r square, here coefficient is 1, here coefficient is minus 6, so r square minus 6 into r plus 9 equal to 0, and we can see that this is nothing but square of r minus 3. This is r square minus 2 into 3, 6r plus 9 equal to 0. Therefore we have r minus 3 times r minus 3 equal to 0, and hence we have real and equal roots. We have r equal to 3 which is repeated, so real and equal roots, and therefore the solution is an equal to alpha 1 times 3 raised to n plus alpha 2 times 3 raised to n, and I have to multiply here by n. This is the modification in the case of distinct roots. If we have distinct roots, then we are writing 3 raised r1 raised to n, r2 raised to n, but if r1 and r2 are equal, we have to multiply by n at one place. So this is the solution of given recurrence relation if we have real and equal roots. So you can see it is very easy to solve the recurrence relations, and if you recall, this theory of solving recurrence relation goes exactly parallel to the theory of solving linear homogeneous differential equations with constant coefficients. You might have understood or you might have seen this type of methods of solving linear differential equations with constant coefficients in the course of mathematics 2. So this theory goes parallel to the method of solving this linear differential equations. Here we have recurrence relation an equal to c1 into an minus 2, an minus 1, and c2 into an minus 2. This I can rewrite as an minus c1 into an minus 1 minus c2 into an minus 2 equal to 0. Now if you recall, here first we are writing auxiliary equation or characteristic equation to solve this linear differential equation, and in that case we replace y by 1, y dash by some power of m, and y double dash by m square. So we first write down the auxiliary equation m square plus am plus b equal to 0, and then we find out roots of this equation, say m1 and m2, and we know that we have three possibilities. M1 and M2 are real and different, M1 and M2 are real and equal, and M1 and M2 are complex numbers. And if you recall, if M1 and M2 are real and different, we have a general solution as y equal to c1 into e raised to m1x plus c2 into e raised to m2x. And if we have equal values of m1 and m2 which are real, then here we multiply by x, c2 times x into e raised to m2x. So same story is here. First we are writing the characteristic equation. So here this is recurrence relation of degree 2. So we write recurrence relation as r square minus c1 into r minus c2 equal to 0. So this is also quadratic equation in variable r, and it has two roots, r1 and r2. If r1 and r2 are equal, we are writing solution as alpha 1 into r1 raised to n plus alpha 2 into r2 raised to n. You can see the parallel things here. Here we have m1 and m2 different, then we are writing e raised to m1x and e raised to m2x, and we multiply them by arbitrary constants c1 and c2. Instead of c1 and c2, we are writing alpha 1 and alpha 2 here. And if we have real and equal roots, then here we are multiplying by x because this is function of x, and here we have function of n, so we are multiplying by n. So this theory of solving linear recurrence relations goes parallel to the theory of solving linear ordinary differential equations with constant coefficients. So both are analogous to each other. I am explaining this so that you can be comfortable by the method of solving linear recurrence relations with constant coefficients, and the method is analogous to the method of solving linear ordinary differential equations with constant coefficients. Okay, fine. So we will continue with the method of solving linear recurrence relations with constant coefficients in upcoming lectures, and I stop here. I hope you like this lecture. Thanks for watching.